Hello all, welcome to this video on distributed computing. Today I'll be talking about spanning tree based termination detection algorithm in distributed computing. Now, let us look into the introduction. The algorithm assumes that there are n processes, pi, which are modeled as nodes where I ranges from 0 to n of a fixed connected undirected graph. The edges of the graph represent the communication channels through which a process sends messages to neighboring processes in the graph. The algorithm uses fixed spanning tree of the graph with process P0 at its root, which is responsible for termination detection. Process P0 communicates with other processes to determine their states, and the messages used for this purpose are called signals. All leaf nodes report to their parents if they have terminated. A parent node will similarly report to its parent when it has completed processing, and all of its immediate children have terminated, and so on. The root concludes that the termination has occurred if it has terminated and all of its immediate children have also terminated. Now, the termination detection algorithm generates two waves of signals moving inward and outward through the spanning tree. Initially, a contracting wave of signals called tokens move inward from leaves to the root. If this token wave reaches the root without discovering that termination has occurred, the root initiates a second outward wave of repeat signals. As these repeat waves reach the leaves, the token wave gradually forms and starts moving inward again. This sequence of events is repeated until the termination is detected. Now we'll see some of the definitions. Now, tokens are a contracting wave of signals that move inward from the leaves to the root. Repeat signals are that if a token wave fails to detect termination, node P0 initiates another round of termination detection by sending a signal called repeat to its leaves. The nodes which have one or more tokens at any instant will form a set S. A node J is said to be outside of set S if J does not belong to S and the path in the tree from the root to J contains an element of S. Every path from root to a leaf may not contain a node of S. Note that all nodes outside S are idle. This is because any node that terminates transmits a token to its parent. When a node transmits the token, it goes out of the set S. Now we'll see a simple algorithm based on this idea. Initially, each leaf process is given a token. Each leaf process, after it has terminated, sends its token to its parent. When a parent process terminates, and after it has received a token from each of its children, it sends a token to its parent. This way, each process indicates to its parent process that the subtree below it has become idle. In a similar manner, the tokens get propagated to the root. The root of the tree concludes that termination has occurred after it has become idle and has received a token from each of its children. Now, this simple algorithm fails under certain circumstances. After a process has sent its token to its parent, it should remain idle. However, this is not the case. The problem arises when a process, after it has sent a token to its parent, receives a message from some other process. Note that this message could cause the process that has already sent a token to its parent to again become active. Hence, the simple algorithm fails since the process that indicated to its parent that it has become idle is now active because of the message it received from an active process. Hence, the root node, just because it received a token from a child, can't conclude that all processes in the child's subtree have terminated. The algorithm has to be reworked to accommodate such message passing scenarios. Now, the problem we saw before is explained with an example here. Assume that process 1 has sent its token T1 to its parent, namely process 0. On receiving the token, process 0 concludes that process 1 and its children have terminated. Process 0, if it is idle, can conclude that the termination has occurred whenever it receives a token from child 2 also. But now, assume that just before process 5 terminates, it is sending a message M to process 1, which is shown here. On the reception of this message, process 1 becomes active again. Thus, the information that process 0 has about process 1, that it is idle, has become void. Therefore, the simple algorithm does not work. Now we look into the correct algorithm. Now the correct algorithm is presented, which was developed by Rodney Topor, and it works even when messages such as the one we saw before are present. The main idea is to color the processes and tokens and change the color when such messages are involved. This idea was suggested by Rodney W. Topor in his work Termination Detection for Distributed Computation in 1984. He works as the Emeritus Professor of Computing Science at Griffith University in Brisbane, Australia. His specialization includes computing science theory, programming languages, database systems, and web applications development. Now we'll see the basic idea. In order to enable the root node to know that a node in its child's subtree that was assumed to be terminated has become active due to a message, a coloring scheme for tokens and nodes are used. The root can determine that an idle process has been activated by a message based on the color of the token it receives from its children. All tokens are initialized to white. If a process had sent a message to some other process, it sends a black token to its parent on termination. Otherwise, it sends a white token on termination. Hence, the parent process, on getting the black token, knows that its child had sent a message to some other process. The parent, when sending its token on terminating to its parent, sends a black token only if it received a black token from one of its children. This way, the parent's parent knows that one of the processes in its child's subtree has sent a message to some other process. This gets propagated, and finally the root node knows that message passing was involved when it receives a black token from one of its children. In this case, the root asks all nodes in the system to restart the termination detection. For this, the root sends signal, that is the repeat signal, to all its processes. After receiving the repeat signal, all the leaves will restart the termination detection algorithm. Now we'll see the algorithm description. Initially, each leaf process is provided with a token. Now the set S is used for bookkeeping to know which processes have the token. Hence, S will be the set of all leaves in the tree. Initially, all processes and tokens are white. As explained before, coloring helps the root know if a message passing was involved in one of the subtrees. When a leaf node terminates, it sends the token it holds to its parent process. A parent process will collect the token sent by each of its children. After it has received a token from all of its children and after it has terminated, the parent process sends a token to its parent. A process turns black when it sends a message to some other process. This coloring scheme helps a process remember that it has sent a message. When a process terminates, if it is in black color, it sends a black token to its parent. A black process turns back to white after it has sent a black token to its parent. A parent process holding the black token from one of its children sends only a black token to its parent to indicate that a message passing was involved in its subtree. Tokens are propagated to the root in this fashion. The root, upon receiving a black token, will know that a process in the tree had sent a message to some other process. Hence, it restarts the algorithm by sending a repeat signal to all its children. Each child of the root propagates the repeat signal to each of its children and so on until the signal reaches the leaves. The leaf nodes restart the algorithm on receiving the repeat signal. The root concludes that the termination has occurred if it is white, it is idle, and it has received a white token from each of its children. Now we'll see an example to illustrate the working of this algorithm. Now in this example, initially, all the nodes from 0 to 6 are white. The leaf nodes 3, 4, 5 and 6 are each given a token T3, T4, T5 and T6. Now the set S will be containing the elements 3, 4, 5 and 6. When node 3 terminates, it transmits the token T3 to 1. Now the set S has changed to 1, 4, 5 and 6. Now after the node 4 terminates, it will send its token T4 to node 1. Then the set S will change to 1, 5 and 6 because the tokens are held only by these 3 nodes. Now node 1 has received a token from each of these children, that is 3 and 4. Now when it terminates, it will send its token T1 to its parent 0. Now the new set S will be 0, 5 and 6. After this, suppose node 5 is sending a message to node 1, causing node 1 to again become active. Since node 5 has already sent a token to its parent node 0, thereby making node 0 assume that node 5 has terminated, the new message will make the system inconsistent as far as the termination detection is concerned. To deal with this, the algorithm execute the following steps. Now node 5 is colored black since it has sent a message to node 1. Now when node 5 will terminate, it will send a black token T5 to node 2. Now S will contain 0, 2 and 6. Now after 5 has sent its token, the node 5 will change to white. When node 6 terminates, it will send its token T6 to 2. Now the set S will contain 2 and 0. Now when node 2 terminates, it will send a black token to node 0 since it holds the black token T5 from node 5. Since node 0 has received a black token T2 from node 2, it knows that there was a message sent by one or more of its children in the tree and sends a repeat signal to each of its children. The repeat signal is propagated to the leaf nodes and the algorithm is repeated. Node 0 concludes the termination has occurred. If it is white, it is idle and it has received a white token from each of its children. Now looking into the performance of the algorithm. The best case message complexity of the algorithm is big O of n, where n is the number of processes in the computation. The best case occurs when all nodes send all computation messages in the first round. Therefore, the algorithm executes only twice and the message complexity depends only on the number of nodes. However, the worst case complexity of the algorithm is big O of n into m, where m is the number of computation messages exchanged. The worst case occurs when only computation message is exchanged every time the algorithm is executed. This causes the root to restart termination detection as many times as there are no computation messages. That's all for now. Thank you for watching.